All right, so we're going to look at the resolution of vectors into rectangular components. So lecture 20 here. Some prior knowledge for this is I strongly recommend you go back and watch the Introduction to Vectors lecture, which was just prior to this, and it will help to have a basic understanding of matrices and Pythagoras' theorem. Key concepts in this video will be unit vectors, resolving a vector into rectangular components in both 2 dimensions and 3 dimensions, the magnitude of a vector in 2D and 3D, and then basic operations on vectors, as well as how we can determine the angle made by a vector within axes. So, sounds thrilling. Let's jump into it. So, resolving a vector into rectangular components. So, the first thing we need to understand about this concept is what a unit vector is. So, a unit vector is a vector with a magnitude of 1. So, if you have some vector A and it's pointing somewhere in space, a unit vector is the vector that points in the same direction but has a size of 1. And the way we denote that is with the vector A, but then we put a little hat on top. And then the way we work out that vector, well, basically what we do is we take the vector, remember that has a magnitude and a direction. If we divide by the magnitude of that vector, then that will give us a vector with a size of 1 in that direction. Okay, so basically you have some vector, divide by the magnitude of that vector. That's dividing by the size of it. Anything divided by itself is 1. So you get a vector with a size of 1 in that same direction. And then we have some special vectors, which we call the component vectors. So the unit vector in the positive direction of the x-axis is called the I vector. And if we look at our little diagram here, that would be this vector here, pointing at the point 1, 0, 0 in our sort of 3D plane. Okay, the unit vector in the positive direction of the y-axis is k, so that's this one here. And the unit vector in the positive direction of the z-axis is k. Did I say k before? I meant to say j before. So that's this one here, pointing with a magnitude of 1 in the z direction. Okay, so in 2 dimensions, we can say the following. The unit vector I as a column vector would be 1, 0. And in the unit vector j would be 0, 1. In 3 dimensions, like we have here, the unit vector I is 1, 0, 0. J is 0, 1, 0, and k is 0, 0, 1. Okay. Okay, now this is an important point about the unit vectors I, j, and k is that they're linearly independent. So what that means is we can actually combine them such that we can get to every point in 3-dimensional space. And what I actually have down here is some sliders. And this blue vector is when we add those vectors together, it's the resultant vector. So when we add 2 groups of I plus 1 group of j plus 1 group of k, we get this blue vector here. And you'll notice we can make all these different combinations, and that blue vector will point in all different directions. And we're not sort of stuck on the plane. We can get to all points in space by adjusting the size of the vectors I, j, and k because they're linearly independent. So yeah, every vector in 2 or 3-dimensional space can be expressed uniquely as a linear combination of I, j, and k. And that's sort of what's going on there. So this example here is, for example, if we had some vector 2, 3, 4, I think you would agree, well, that's just going to be 2 groups of vector I plus 3 groups of vector j plus 4 groups, 4 groups of unit vector k. And then so when you combine them, you get that blue vector there that's pointing to that position in space. Again, because they're linearly independent, we can combine them however we like to get every vector in 2 or 3-dimensional space. And this obviously shows us in 3-dimensional space. Okay, this is in contrast to linearly dependent vectors that we spoke about in the previous video, where you're kind of stuck in 2 dimensions on a line, or in 3 dimensions, you're stuck on a plane because you're linearly dependent. But because these are linearly independent, you can get everywhere, which I think is pretty cool just by combining them however you like. So that is what it means to resolve a vector into rectangular components. You're sort of just doing this operation. You're multiplying the unit vector by a scalar quantity to get any vector you like. Okay, so in 2 dimensions, let's have a look. It might look something like this. So for the point P, which is at some coordinate x, y, the vector OP is x multiplied by the unit vector I plus y multiplied by the unit vector j. So for example, here you can see that this point here is clearly at 4, 4. So this unit vector would be, sorry, this vector would be defined as 4i plus 4j. And that would be your vector OP. And similarly, the magnitude of that vector OP is, well, you can just make a right angle triangle, can't you? And then you apply Pythagoras' theorem. So this height here is 4, and this sort of length here at the bottom is 4. Applying Pythagoras' theorem to a right angle triangle, the square root of 4 squared plus 4 squared will give you the magnitude of this vector P, vector OP. So that's how we do it in 2 dimensions. If we look at 3 dimensions, all the same rules pretty much apply. So now we've just got some point in space, but it's now defined as x, y, z. You're in 3-dimensional space now. So again, the vector OP is x multiplied by I plus y multiplied by vector j plus z multiplied by vector k. And so in this example, I think we can probably see that the x coordinate is 1. The y coordinate seems to be 2, just reading from here, and the z coordinate seems to be up here at 3. So this, in rectangular components, this particular vector would be vector I plus 2j plus 3k. And similarly, to find the magnitude of that vector, we apply Pythagoras in 3 dimensions. Pythagoras works in any n-dimensional space. So the magnitude of vector OP will be the square root of x squared plus the square root plus y squared plus z squared. And so that's how you would find the magnitude or the length of this vector in 3 dimensions. So I think that's pretty cool. Let's have a look at the next thing, which is now we're applying basic operations on those vectors. So if we have a look at our 3-dimensional space here, again, yeah, we're obviously in 3-dimensional space. Let's imagine we've got 2 vectors. The first vector is vector u, and it's defined as u1 multiplied by I plus u2j plus u3k, and v is similarly defined. But these are 2 separate vectors. If we needed to add those vectors together, you just add the coefficients of the respective unit vectors. So if you were to do vector u plus vector v, you would just add u1 plus v1, and then obviously multiply by the component vector, the unit vector I, which is the unit vector in the x direction. Okay. Similarly, if you needed to do vector u minus vector v, you just subtract the coefficients for each term. Okay, so before we talk about this part here, let's just do an example. So let's imagine that this line here is vector u, defined as at the point 1, 2, 3. So we can see it's got an x value of 1, a y value of 2, and a z value of 3. And similarly, this vector v over here is 3, x value of 3, y value of 2, z value of 1. And so if we were to add those vectors together, you just add the coefficients. So it's going to be 1 plus 3 gives you 4i, 2 plus 2 gives you 4j, plus 3 plus 1 gives you 4k. So that vector in orange now is 4i plus 4j plus 4k. And so the end point of that vector would be at 4, 4, 4. And so that's how you add those vectors together. Okay, and the other thing to just say is if you're multiplying your vector u by some scalar, it's just multiplying the coefficients of each term of each unit vector by that value m. So essentially that's just going to scale your vector up or scale it down, make it larger or smaller. Okay, so that is operations on vectors. You can think all the same rules apply in two-dimensional space as well. So we've obviously done this example in three-dimensional space, but the same is true in two-dimensional space. Okay, the last thing we'll look at is the angle made by a vector with an axis. So if we do have some vector u, again, it's defined as u1i plus u2j plus u3k. It makes an angle of alpha, beta, and gamma with the positive directions of the x, y, and z axes respectively. Okay, then what we can say is cosine of alpha equals the coefficient of unit vector I divided by the magnitude of the vector. So I think an example will be instructive here. So we've got some vector u that's pointing at this point here, A at the moment. And what we want to do is we want to find the angle that that makes with the positive direction of the x-axis. So what that means is we've got this vector. We want to know what is, if I get this lined up properly, what is this angle here, the positive direction of the x-axis? And what we're saying is this is how we do it. And it should make some intuitive sense, and I think you'll see why. So let's imagine we've got this vector, 2i plus 3j plus 4k. Okay, cosine of alpha equals u1 over u. And that should make sense because what we're saying is, if we look at it from this view here that we've got, we can see that the x value is 2. And so what we're going to get is we're going to get a right angle triangle like this. And we know from SOHCAHTOA that cosine of an angle is the adjacent over the hypotenuse. Well, the adjacent side length is 2 because that's the x-coordinate. And the hypotenuse is just going to be the length of that vector. So we get that the angle in here, cosine of this angle, is 2 over the magnitude of u. Okay? So we can set that up. So we get cosine of alpha equals 2 over the magnitude of the vector u. Now remember, the magnitude of vector u is the square root of the coefficients of each respective unit vector. So it's going to be over the square root of 2 squared plus 3 squared plus 4 squared. So that's cosine alpha equals 2 over all of this equals the square root of 29. And then obviously to find an angle, you take the cosine inverse. It gives you 68.2 degrees as this angle here. And we could apply the same logic to finding the angle between the y-axis and the z-axis. So let me just show you what that looks like to show you that it works. We can actually find the angle here. And it says beta, but ignore that. It should say alpha. But yeah, you can see it's 68.2 degrees is that angle there for alpha. Okay, so yeah, that's how you find an angle made with a vector, made by a vector with an axis. So hopefully you found that useful. That is resolving vectors into their rectangular components. If you did find it at all helpful, please give us a thumbs up or consider subscribing. We're almost at 100 subscribers, so that's not very many, I know, but for me, it's something. So if you want to see more of this, let me know. And if you need any private tutoring, get in touch. So talk soon.